Okay, so we just did the kind of intro to matrices. Let's continue. Simple examples of matrices. We have what are called square matrices. Which just means I have the same number of rows as columns. I'll give you some quick examples. I could have 1, 2, 4, 3, let's say. That's a square matrix. It's a 2 by 2. Okay, let's choose another one. Let's choose 1, 2, 3, 7, 8, 9, 6, 5, 4. Okay, that's 3 by 3. Okay, which I'm sure you can understand. Okay, there's something called a diagonal matrix. Which is a square matrix. Which is 0 off the diagonal. And what does that mean? Okay, well, the thing that is considered the diagonal of the matrix is the one that goes from the 1, 1 entry down to the n, n entry. So in that case, the one that goes, in this case here, the one that goes from the 1 up in this upper left corner to the 4 in this lower right corner, or which follows the line of that marker there. Okay, so give you an example. I could have one, let's take the same diagonal entries, 1, 8, 4, 0, 0, 0, 0, 0, 0 off the diagonal. That is a diagonal matrix. Okay. There is something called the unit matrix, which is very special. Okay. More often called the n by n identity matrix. Okay, what is that called? Or what does that look like? That is a diagonal matrix with 1s on the diagonal and 0s everywhere else. Okay? And then there is the null matrix, also called the 0 matrix. So I would have, how do I write that? There's no standard notation. I've seen it written like that, 0 with a little bar next to it. I've also seen it written as 0 with an underline, although some people use that for 0 vector. There's no standard notation for this one that I'm aware of, but the matrix is very simple, of course. This is the 3 by 3 0 matrix, and it is just a 3 by 3 matrix with all zeros. Okay. And of course, a 0 matrix can have any dimension, okay, any m for any number of rows, any n for any number of columns. They do not need to be the same. However, the identity matrix is always assumed to be a square matrix. It doesn't really make sense to talk about identity matrices when we don't have square matrices. Okay, these are two special properties. If A is any n by m matrix, and you know what, I'll use this 0 notation here. 0 is the n by n 0 matrix. Well then, A plus the 0 matrix is the same as A, which is the same as 0 plus A. Okay? It doesn't matter if I add 0 on the left or the right. Adding zeros doesn't change anything. And if A is an n by n matrix, and I is the n by n identity, or unit, well then A is the same thing as I multiplied by A, which is the same thing as A multiplied by I. So the 0 matrix behaves in the same way as the number 0 does for numbers. Add 0 to any number, you get the same number. You know, so 3 plus 0 is still 3. I still get the same number. It's the same for matrices. The 0 matrix added to any matrix A, same matrix. The identity matrix works like the number 1. You multiply any matrix, any n by n matrix by the identity matrix of the same size, you get back the same matrix. 7 by 1 is 1, which is the same as 1 times 7. Okay, so that leads us to something pretty important, which is the idea of determinant. Okay, I should say, so we have addition, okay, and we have multiplication. So okay, so what's the general pattern of, just for numbers? Okay, addition. Say we have A, and we add 0 to it. That's the same as A, which is the same as 0 plus A. Great, okay? And 0 is the same thing as A plus its negative, okay? Which is the same thing as the negative plus the number A there, okay? And the way we could say this is that minus A is the negative of the number A. That makes perfect sense. Okay, and then we have multiplication. Okay, we would have A by 1 is A, which is the same as 1 times A. Okay, so multiply 1 on either side, it's the same. And then I would have A multiplied by 1 over A, the reciprocal or multiplicative inverse. Well, that's 1, which is the same as 1 over A, and that multiplies by A on the other side. Okay, so this is true for numbers, okay? And there's one exception which I'll talk about. This is true for every number A. A plus 0 is the same as A, which is the same as 0 plus A. This is true for any A at all. Positive, negative, doesn't matter. This is true. These addition ones, these are always true. The multiplication ones are a little bit more complicated, but not significantly so. A times 1 is always A for any number A, and 1 times A is always A as well, okay? Sorry, I'm going a little bit hoarse. Okay, so what do I, always true, always true, always true. This one is a little bit different. Why? This one is not always true because 1 over A is not always something that exists, okay? 1 over A, this one, is for all A sorry, I should say for all lowercase a, which are not 0. Okay, otherwise that doesn't make sense. Okay, and I've said this before, probably to all of you. I don't think that there is such a thing as subtraction. I don't think that there is such a thing as division. Well, I know that there is such a thing as subtraction and such a thing as division. I don't really think about them that way. For me, if I have a minus b, what that really means is a plus the negative of b. So I replace subtraction with the addition of a negative, and I replace a divided by b in my mind by a multiplied by the inverse of b. Okay? So for me, there is no subtraction, there is only addition of negatives. For me, there is no division, there is only multiplication by inverses. Okay, the problem is that, of course, I can't divide by 0, okay, because 1 over 0 does not exist. Okay, we can't divide by 0. And the way we say this is that 1 over 0 doesn't exist. It's not a sensible thing. Okay, but that's not really the big takeaway. The big takeaway is that 0 doesn't have an inverse. Okay. Zero has no inverse. Okay, so 0 is the only number that doesn't have an inverse. Okay, in the context of normal numbers. Okay, but matrices work a little bit differently. Matrix addition is almost exactly the same. Okay. You can see here that matrix addition, this will work for anything. Every matrix can have a negative. All you do is just change the sign of all the elements. Matrix division doesn't really make sense. Okay, it's not a concept that is particularly useful. So we replace the idea of matrix multiplication, matrix division by the idea of multiplying by an inverse. So if I want to divide in air quotes, if I want to divide matrices, what I really mean is I need to multiply by an inverse, and if I'm going to do that, I need to know if the inverse exists. So the determinant of a matrix is a measure. It's more than that actually, but it's in this context it's perfectly fine to limit our scope to this. The determinant of a matrix is a measure of whether the matrix is invertible or not. Okay, we'll talk a little bit more about it. It's really just a special value that's associated to every square matrix, and we'll talk about the forming of determinants probably in the next video. Okay, but here's the basic idea. We write let A be a matrix. Okay, we're going to write the determinant of A as det A. This is the determinant of A. Okay, det A is the determinant of A. Okay, and here's the big important rule. Okay. A has an inverse. if and only if, so these arrows go both ways. If A has an inverse, it means the determinant of A is not the same thing as 0. And if the determinant of A is not the same thing as 0, then we know that A has an inverse. Okay, so this goes both ways, back and forth. Kind of a two-headed arrow is what I intended to draw there, even if it didn't come out very clearly. Okay, so that's something that's important to know. Okay, if the determinant is 0, no inverse. If we have any other value for the determinant, then the inverse exists. Okay. Why would we want to divide by matrices? Okay. Well, I'll get into actually calculating determinants in a little while, but just for the moment. Okay. Suppose we have the matrix. Actually, suppose we have a system here. Suppose I say I have 3x plus, let me pause for a moment just so I can get a really good example here. Okay, so here's the example I've written down. 3x plus 5y is equal to 1, and then I had a bit of a mistake here with my handwriting, and then I wrote down the other equation. I want 2x minus y equals 5. And that is a system of equations, and we know how we could solve that. We've all done this before. But one way that I could solve this is to say, okay, well, I have this system of matrices here, which represents this problem. Say I have 3x plus 5y equals 1, like that. And I have 2x minus y is 5. I can translate that to a system of matrices which encodes the same information. Okay. Okay, so this is my original system here. And I'm translating that to a system of matrices, which I'll write over here. Okay, where I take the rows of my matrix from here. Okay, so my first row for a 2 by 2 matrix here is going to be 3 and 5, because those are the terms that appear. And then I have 2 and minus 1, because those are the multiplications of the x and the y there. That's going to multiply a vector of x and y, and it's going to give me a 1 and a 5. And this is consistent with the nature of matrix multiplication. In fact, if I multiply this out and I go row by column, I would have 3x plus 5y. Then I would have 2x minus 1 times y, so that would be 2x minus y. And then that would have to be equal to 1 and 5 on the other side. And I would have the same information that I had on the matrices here. So if I were to let A be equal to my matrix 3, 2, 5, minus 1, like that. Let's say I let we'll let x, capital X, be lowercase x and y, just the vector of the two of those. And let's let B be 1 and 5. Then I have the matrix equation AX is equal to B, like that. Okay. AX is equal to B. And now, how can I solve this? Well, what I'm really trying to find is the x and y here, or this vector x of the variables lowercase x and lowercase y. Well, suppose I multiply both sides by the inverse of A. And then I would have A times AX, A inverse times AX would be A inverse times B. Okay, like that. And then I would have A inverse by A times X is equal to A inverse times B, just moving from one line to the next. But this is the identity matrix. Okay, but the identity matrix multiplies and leaves everything the same. So this just gives me A inverse B. Okay, so finding a matrix inverse allows me to find a solution to this system of equations. So the question is, can I actually go and find the inverse? Okay, And just as a really quick reminder, I'm going to do the 2 by 2 case, which won't take me very long because we have a formula for our matrix inverse. Okay, so if A is equal to A, B, C, D, you all saw this last year. Okay, I didn't teach it to you, but I know you all saw it last year. Then if A inverse exists, okay, A inverse is equal to 1 over the determinant of A. And then there's a form on this matrix here. What we do is we switch the position of the D and the A, and we change the sign of the other two, where the determinant is A times D minus B times C. Okay? A times D is minus B times C. Okay? So, pretty simple for me now to actually go and work out the inverse of this matrix, provided it exists. And of course it will. The determinant here is chosen to be something that will work. The determinant of A then is the number that can't be 0. Why can't it be 0? Well, if it's 0 here, I would have 1 over 0, and of course that means division by 0, which isn't allowed. Okay, so my matrix, everything works fine, provided this one term doesn't get mucked up, which is easy to do. Okay, let's look at my original matrix here again. My matrix was 3, 2, 5, minus 1. Okay, so if I use that pattern, okay, which I'm just going to leave up there, okay, A was equal to 3, 2, 5, minus 1, reading the columns, okay, well then A inverse, provided it exists, is going to be what? I have 1 over, okay, now I have the A times D, so that's 3 times minus 1. Okay, then I have 5 times 2. Okay, 3 times minus 1 times minus 5 times 2. Fair enough. Okay, and now I have my switch. Okay, so I switch the 1 and the 3, the minus 1 and the 3, and now I change the signs here. So I have minus 5 and minus 2, like that. Clean that up. This is 1 over minus 13. Okay, and then I have minus 1, minus 5, minus 2, and 3. If I write it this way, I have to have 1, 2, 3, 4 minus signs. So if I might choose to multiply the minus sign in through, which in fact I will. Okay, and what do I end up with? I end up with 1, 5, 2, and then I only need 1 minus sign, which is over there. Okay, so this is generally my preferred way of writing this. I have a scalar multiple of 1/13 sitting on the outside. I would not multiply this through, because if I multiply this 1/13 through, then everything inside has to be over 13, which means I need to write 4 fractions instead of 1. Okay, and that's bad compression. Okay, here the reason I've chosen to multiply through the minus signs is because I have 1, 2, 3, 4 versus 1. Okay, I would always prefer to switch things around so that I have less minus signs, because less minus signs means less possibility of minus sign mistakes in calculation. Okay, so this is my A inverse, and B was the matrix what? B was 1, 5. So A inverse times B is equal to 1 over 13. Keep that on the outside, don't do anything with it yet. 1, 5, 2, minus 3, this time reading the rows. And then I have 1 and 5, like that. And this is trivially simple to solve here. Okay. What do we have? Okay, we have 1/13 sitting on the outside. This is x, by the way. This is the thing I'm actually trying to find. Okay. That means x then is equal to what? I have 1/13. Okay, and now matrix multiplication here goes row by column. So I have 1 times 1 plus 5 by 5. Okay, and I have 2 times 1 minus 5 times 3. Okay, what do I have? This is 1/13 still on the outside. Always leave that to the end. This is 1 plus 25, which makes 26. This here is 2 minus 15, which gives me minus 13. And of course, multiplying through, this gives me 2 minus 1, which tells me that x was 2 and y was minus 1. Okay, so that is what I can do with matrices once I have their inverses. Okay, so it is valuable to me to be able to find their inverses. And we'll talk about how to find the inverse in the next set of videos of a 3x3 matrix. Okay, so this was a 2x2 matrix. The reason we teach this in first year is because it's relatively simple and it gets the idea of a matrix across. But it doesn't really help understand how the inverse matrix is actually constructed. This is kind of given to you as a formula, okay? And then you're just kind of supposed to learn it or refer to it and be able to use it. But there's more that goes into the actual construction. We'll see in kind of more detail. So we'll talk about 3x3 determinants and 3x3 inverses in the next video. So next video. Three by three determinants and 3x3 inverses. Now I say next video, I really should say next videos. This will probably take one video all by itself, and this will certainly take one video all by itself. So I think I have maybe 3 videos that I still have to make for you. So that would come to about an hour and a half's worth of content. I'll try to get that all done for you tomorrow. Okay. Regards, hope you're all well. And, you can email me if you have any problems. Okay. Bye, everybody.